sense the angle of the motor and then use that angle to come up with velocity, don't we? Okay, so I probably won't get all the way done. I got 10 minutes here, but let's look at what does these optical encoders look at. And there's all sorts. Where am I at? I'm going to go to here. So, do I have the picture? There we go. And I'll let you look at, I want you to look at the motor on your robot when you get to lab. Sometimes there's a little disc on the end. So I don't know if you've seen your motor, you probably haven't looked at it too much, but what's going to attach to your wheel is the output shaft. And then the output shaft's connected to a 30-to-1 gear ratio gear head. And then there's a little tiny motor on the end of all that. Okay? The gear head's probably the biggest weight of your motor. Well, they're probably about the same. But then we got this little motor. And coming out the back end of the motor is a shaft. Okay? So that our little motor is spinning 30 times to make our output shaft turn 1 revolution, right? So it's spinning a lot faster than our output shaft of the motor. Well, on the end of that little motor, its back shaft, there's a little disc. That disc actually has 5 north-south poles in it, okay, for sensing. And then on the little circuit board that's back there are little Hall effect sensors that when the magnet goes over that Hall effect, that says, hey, I see a flux, and the signal goes high. And when it goes away from it, away from the North Pole or whatever pole it is, it goes low because it's gone. It's that sensitive. And then as the next pole comes across, it goes high. And then as it's gone, it goes low, right? See kind of what that's doing? Well, that's the same thing in an optical encoder, okay? These magnetic coders are nice, but you can imagine that there could be situations where you've got so much magnetic flux from your motor and all this kind of stuff that things get confused. But it doesn't seem to be too big of a deal. But there's another kind of encoder. This was kind of come up with first, I think, this idea of an optical encoder. And they're the same thing. They give you the same signal. Another way to think of this, and maybe see if I can draw it about the same. So this disc that is right here is what would be attached to the back end of your motor. So this shaft right here would be attached to your motor right here. Okay? And as the motor spins, this disc spins, right? Now, the sensing, what's going on there? Let's see if I can try to draw it. So you got this disc. Again, you got your shaft coming out here. The shaft or whatever coming out here, and then there'll be another shaft or whatever. This is attached to the motor. You know, this output shaft wouldn't necessarily need to be there either. Somehow this disc, though, is attached to the motor. All right, then what they do with optical encoders, they photo etch these. So they're really nice and precise, and they etch slits, openings, all around this wheel, okay? And using photolithography, they can get them exactly the same distance all the way around. And the number of slits, you know, is kind of the cost of the encoder. Less slits are usually a little bit cheaper optical encoders. More slits, same with the magnetic encoders. If you had more north-south poles on your disc, they would be more expensive, okay, harder to manufacture. So, you know, I have some that have 500 slits per revolution, 1,000. I got an encoder that's got 1250 slits per revolution. You know, I've seen them as high as 15,000 slits per revolution on really expensive ones. Anyway, so they're in there all the way around, right? All the way around the disc. And sometimes there's actually 2 sets. Depends on the manufacturer who's making these. And then they make these little devices. They're little opto interrupters. So I'm trying to show you that they go on either side of the disc. And that's kind of what this is showing. So on one side of the disc, you've got LEDs that are producing light. They're always on, okay, usually. They can be infrared, they can be colored, whatever works the best for this sensor. And then over here are photo transistors. That when they see light, the transistor's turned on. When they don't see light, the transistor turns off. Okay? So you can imagine you can make a pretty nice square wave, can't you? When it sees light, the output of that transistor goes high. When it doesn't see light, it goes low. Just like the magnetic encoder was with the Hall effect. When it sees a magnetic field, it turns on. When it doesn't see the magnetic field, it turns off. Okay. So again, what's the goal of our encoder? The goal of our encoder is to give us an angle that the motor has turned to, right? Okay. So let's just think, what if we just had one phototransistor here? What could we do with this information that we have here? Goes high, goes low. Goes high, goes low. We could count, for example, we could set up something, you could set up an external interrupt, for example, in your microcontroller, in the 28379D board. And you can say every time something goes high to interrupt you. That's a little crude, but you could do that. You could sense when it goes high, and then all the interrupt would do is increment a count. And every time it sees that pulse go high, you keep on incrementing that count. And because we know how many of these square waves are per one revolution of the wheel, right? Because that's the number of slits, we can convert that count to radians, couldn't we? Because if it's a 500 slit encoder, you get 500 counts per one revolution, don't you? The problem is, what if we take that motor and spin the other way? Don't we keep on just getting high edges? There's no difference, is there? So by using just one square wave, one phototransistor, you only can figure out one direction of spin. And I would call that kind of just a single signal, I would call that a digital tachometer instead of an optical encoder. Digital tachometers, how does a tachometer work on some crude systems? You can just put a proximity sensor that's measuring when a tooth of a gear comes by that proximity sensor, right? And so you have this gear that's spinning with the motor, and each tooth, boom, 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 is being seen by seen and then not seen, seen and then not seen by the proximity sensor. And again, the frequency of that square wave then is produced by that proximity sensor can give you velocity. But you only know that velocity, or the angular velocity of the motor, in one direction. So if you got a motor that only spins in one direction, great. That's fine, right? You can even do it with just a single swipe. So something on your motor, you got a proximity sensor here, and you got one tooth of the gear, and boom, when that happens, and then the next revolution, and the next, you get a pulse. And if you measure the time between those pulses, you know how fast the motor's spinning. So I call that a tachometer. With an optical encoder, we need to know if we're going in the positive or negative direction, don't we? That'll be nice to tell the motors of our robot to go forward or to go backward, won't it? We want to know. Also, by the end of Lab 7, I'll want you to tell me where the SegBot is XY on the floor. And sometimes the SegBot's going to go backwards, right? And so you need to know what angle the wheels are at, both positive and negative. So that's where what they do, I'm running out of time, we'll talk about this on Monday. That's why they actually have a second transistor, and they locate it strategically so that the square wave of, we call this channel B and channel A, we do this such that the channel B's square wave is 90 degrees out of phase of channel A. And then notice there's 4 states of these signals. There is when B is low, A is high. A is high, B is high. A is low, B is high. A is low, B is low, and then it repeats. Okay? So that chip I showed you, and also this peripheral inside your 28379D processor called the EQEP, Enhanced Quadrature Encoder Peripheral is what that stands for. Its job is to monitor the state of these two and increment a count. That's its life. Again, we do a lot of counting in CPUs, you're figuring out, don't we? Counting of clocks. Here we're counting a sensor. And what we do is when we see it go from high-low to high-high, the peripheral does, when it's doing that, when it sees that, it increments a count. When it sees it go from high-high to low-high, it increments it again. But now if it stops, well, it doesn't not worry about stop, but if it happens to go from low-high to high-high, going the other way, it decrements the count. Okay? Anyway,